This is an example of the segment addition postulate being applied to set up and solve an algebraic equation. So in this example, our job is to find AB and BC. We're looking for the lengths. Now, when I'm looking at this image, I want to note what I see. I see segment AC, which is broken up into two smaller segments, AB and BC. Segment AC is my large segment, and segment BC, or AB rather, is my first segment, and segment BC is my second segment. So when I'm setting this up, I want to think about the segment addition postulate, which tells me that if I have segment AC broken up with segment or point B on segment AC, then segment AB plus segment BC equals segment AC. So I need to think, okay, what are the lengths that I know? Well, I know that AB is indicated by 9x plus 7. So AB equals 9x plus 7. I'm going to hang on to that because this is going to come up later when I actually need to find the length of AB, because the first thing I need to do is solve for x. So I want to hang on to that equation. I know BC equals negative 3x plus 20. So both of these are indicated by the algebra in the diagram. And I know that AC is 39 as indicated by once again, the label in the diagram. So AC is 39 units. So now I replace. So typically I like to start by replacing things inside parentheses and then moving things around as needed. So 9x plus 7 goes in for AB, or this AB can be substituted by 9x plus 7. Negative 3x plus 20 substitutes BC. And 39 substitutes for AC. So now I'm thinking algebra. So this is just a straight up algebraic equation now. 9x plus 7 plus a negative is negative, so minus 3x plus 20 equals 39, and I solve this as I would any other algebraic equation. So when I'm looking at this algebraic equation, my first step is to combine like terms. I know that 9x and negative 3x are like terms, so 9 minus 3 is 6, so they combine to make 6x. I know that positive 7 and positive 20 are also like terms. 7 plus 20 is 27, so they combine to give me 27. So I've now changed this to a two-step equation. I can use my normal processes of reversing my order of operations. So I'm going to start by attacking addition or subtraction. I see an addition. I attack that by turning it into subtraction. I invert the operation. 27 minus 27 will cancel out. 39 minus 27 is 12. And I bring down my 6x. I continue on. The last step here is to divide both sides of my equation by 6 to then solve for x. And so I know that x equals 2. 12 divided by 6 is 2. Now, I've got that part not done yet because I still need to solve. If I remember back to my job, I need to find A, B, and B, C. So this is where I now solve. So AB is 9x plus 7, but I know, based on what I solved, that x equals 2. So if I remind myself, hey, x equals 2, I'm going to substitute that in to my equation. So AB equals 9x plus 7, 9 times 2 plus 7. When I do 9 times 2, I get 18. plus 7, and 18 plus 7 is 25. So AB equals 25. I indicate that this is done by putting it in a box indicating that that is my correct answer. And then BC is negative 3x plus 20, so I will now solve for BC. BC equals negative 3x plus 20, but instead of x, I'm putting in 2 once again. I'm substituting it in. Negative 3 times 2 is negative 6. Negative 6 plus 20 is 14. And then I can double confirm this because 14 plus 25 is indeed 39, meaning that I have my segment addition postulate still works. AB plus BC, 25 plus 14 equals AC, 39. So now I have solved my segment addition postulate, or solved this problem using the segment addition, this algebraic equation using the segment addition postulate. I have found AB and I have found BC, but I had to first solve for x using the segment addition postulate.